Hello everyone, welcome to this lessons learned video. Today we're going to talk about electromagnetic radiation and do some problems about them. So this first one asks, what is the frequency of 20 millimeter microwaves? There's a very simple equation that relates the speed of a photon, basically of light, to its wavelength and frequency. So c, which is the speed of light, and again c is going to be, in vacuum it's going to be 3 times 10 to the 8 meters per second, is going to be equal to wavelength times frequency. Okay, so the wavelength of the wave is if you do this, or if you have the wave, we should plot it a little better maybe. The length of a single cycle, so how much does it travel in space as it goes through one cycle? That's wavelength. And the frequency is how many times in 1 second, how many cycles happen in 1 second. Okay. So if you multiply those two numbers, you will get the speed of the wave, which is for light is always going to be this. Okay, so it doesn't have any mass, but it's got energy. And the speed is always constant. We're told that the microwaves are 20 micrometers, or not micrometers, millimeters, right? Now 20 millimeters is the same thing as saying 2 times 10 to the negative 3 meters. You always want to make sure your units here are SI units, so meters or hertz for frequency, which is the same thing as 1 over seconds. So when we solve for a frequency, it's a very simple problem. We're going to get 1.5 times 10 to the 10 hertz. Okay, so every second, right, this photon goes through 1.5 times 10 to the 10th cycles. Here it says, how long does it take the signal from a local radio station to travel 20 miles? So radio waves are same thing as light. So they're electromagnetic radiation. And although we can only see a specific wavelengths of electromagnetic radiation, all the other wavelengths, outside the visible light spectrum are going to still travel at the same exact speed, which is 3 times 10 to the 8th. I need to look up what a mile to a meter is. Okay. So we're told that we're trying to travel 20 miles. Now we want to use in meters because that's the unit usually for physics, and our speed of light, which is this right here, it's in meters, right? So we don't want to use miles. So a mile is 1,609.34 meters. Now we're trying to get time, right? Because they're saying how long it takes, and we have this value. So what we can do is rewrite this as 3 times 10 to the 8 meters per second. It's the same thing as what we have up here. If we want time, we want to put the seconds on top. So we're going to multiply this seconds on top and 3 times 10 to the 8th meters on bottom. And this meters is going to cancel out with this, and the miles are going to cancel out. And then we will get very low numbers, so we will get 1.073 times 10 to the negative 4 seconds. So that is very fast. Right? This one asks, what is the wavelength of a 902.9 megahertz radio wave? So we're going to use the same equation as before. The speed of light is 3 times 10 to the 8th. The wavelength is given in megahertz. Now megahertz is going to be 3 times 10 to the 6th of hertz. So this is the same thing as saying 92.9 times 10 to the 6th. And let's make sure that's correct. So this is, yeah, that's right. Then we have the frequency, which is given to us here, right? But we would want to find wavelength. So when you solve for wavelength, we will get 3.229 meters, which is a very long wavelength. So the frequency is relatively low, though. What is the wavelength of light waves if their frequency is 5 times 10 to the 14 hertz? So once again, speed of light waves on the left. We have the frequency, which is 5. Let's do this first. We're trying to find wavelength, right? Frequency is 5 times 10 to the 14th hertz. So when we divide both sides by this, we're going to get 6 times 10 to the negative 7 meters. Usually when you get a range kind of like that, you can write it as 600 nanometers also. So both are correct. So now we get into some of the properties of electromagnetic waves that deal with energy. So it's important to introduce some new concepts. As an electromagnetic wave travels through space, it's going to have two components. It's going to have the electric component. So the electric field of it, if you don't know what electric field is, then you should watch the other videos we've done. But basically going to have an electric field. And as it travels through time and it travels through space, this electric field is going to go up and then it's going to go down. Going to go up and go down. Right? It's also going to have what's called a magnetic component. So the magnetic field of it is going to be kind of perpendicular to this, and it's also going to go up and down and up and down in these directions. Okay. Now, let me make sure I've drawn that correctly. Yeah. So they kind of travel together in that way. Now, each field, the magnetic field and the electric field, is going to have a certain amount of energy that is associated with it. So that energy, we usually don't really call it energy, we call it intensity. Okay. Now, intensity, what that means is the units for that is watts per meter squared. And you might be wondering, what does that mean? Watts means joules per second, and meters squared is just area. So how much energy? The question we're asking is, when you want to find intensity, we're saying, how many joules per second am I carrying through how much area of space? That's basically what this intensity tells us. So you should always keep in mind what it means, right? It means power, which is, again, watts, or same thing as joules per second, over the area of space. Now, that's one way to think about intensity. There are certain formulas that tell us the intensity of an electromagnetic wave when it comes to, relative to both fields. So the magnetic field will have its own intensity and the electric field will have its own intensity. So that of the magnetic field will look something like this. we're going to have what's called the average intensity. Okay, because the intensity changes because these things oscillate, right? One goes down and up and down and up. But the average intensity is going to be found like this. For the magnetic field, this is going to be the equation. Now this might look intimidating, but basically, c is the speed of light, right? It's a constant. It's always going to be the same. And so this right here is another constant that is going to be associated with magnetism. So the value of this constant is the permeability of free space. So this is going to be 4 pi times 10 to the negative 7th, and the units are newtons per amps squared. You don't really need to worry too much about the units. And then we need to talk about what this B is here. B is generally, it just means magnetic field. So it's a certain value, and it's going to be in the units of Tesla. Now you can see that there's two distinct things. We have B naught and we have B RMS. What do these mean? So let's extract out the magnetic field here and just look at that alone, right? So let's say we'll only look at the magnetic field for now. If I were to try to, so this is one cycle of it, but there are many cycles. If I were to try to find the maximum of the magnetic field, I would just measure here. I would go like this, and I would find the maximum magnetic field. And that's what this value is. So this value here, I should probably put it down here, is the maximum magnetic field. However, what if I want to find the average magnetic field, not the maximum? Okay. What I could do is take the average of all of these values here. But if you notice, if I take the average, something interesting will happen. Let's overlap this first part of the cycle with the second part of the cycle in a new one. What you can see is that we have what's called destructive interference. It's not really what's occurring here, but when you do the math, it cancels out. So if you take the average of all of these and add them to the average of all of these, it'll just become 0. So that's not very useful, right? So instead what we do is try to take the average of it, kind of like the average of just this part. So the average just here. So we'll be somewhere around here, right? That'll be about the average. So that's called the RMS. So we can't really do the average because it oscillates, but we kind of cheat in a way and we find the average a different way. So that's what RMS means. It means average magnetic field. So now let's write that down. So these are the equations for the magnetic field. So you should write these down and do some practice problems and understand them. And we'll do a few here. Now for the electric field, it's going to be very similar. For the electric field, let's erase these. Okay. For the electric field, the intensity of it is going to equal E naught C. It's not really E, but it's a weird Greek letter. Now, so again, we have a few constants. C is the same. It's the speed of light waves. Then we have this value here, E naught. It is called the permittivity of free space. I apologize. So basically it's going to be 8.85 times 10 to the negative 12th. The units here are c squared, which is coulomb squared, which is unit of charge, over newtons meters squared. Don't really worry about too much the units there, just for reference in case you need it somewhere. And then same thing again. E naught is the maximum electric field in this case, as opposed to magnetic field. And then E RMS is average electric field. So that's basically how this works, and you should write these equations down so you know them. In this problem, we're asked about the maximum electric field. So what we need actually is this equation, right? So I'm going to delete everything else so that because we don't want to run out of space doing this problem. So we need the maximum, not the average, right? This would give us the average. So we don't want the RMS or the average, so just get rid of this for now. So we get this expression. Ooh, that's not good. Okay. We're told that the magnetic wave, electromagnetic wave, radiates at a rate of 150 watts per meter squared. Whenever you see this watts per meter squared, that's intensity, as I've explained. So this is 150. And then we have E naught in the equation, which is 8.85 times 10 to the negative 12. And then we have the speed of light. And then we have the maximum electric field squared. So you can then solve for the maximum electric field and get the answer because that's what they're asking for. So this is just a little calculator skill here. All right, let's check this. Yep. So the value that you get when you do this on the calculator is the maximum electric field is 336. But again, we need a unit for this. For electric field, you can either use newtons per coulombs or volts per meters. Both are correct units for electric field. Okay, so this is your answer.